Welcome to video series on acid-base balance. This video is on regulation of pH first. Now we have three different mechanisms to regulate the pH inside of our body. The first one are the buffers, which constitute the first line of defense, and these include the bicarbonate buffer, phosphate buffer, and the protein buffer. And the second line of defense is by the respiratory mechanism and the renal mechanism. Now, why is the need to have three different mechanisms to regulate the pH? This is because the buffers act within seconds. They react with acids and bases and thus resist the change in pH, but they do not go for completion. So the second line of defense is the respiratory regulation, which will take few minutes to come into effect, but this regulates by removal of carbon dioxide. However, respiratory regulation will also not go for completion. The final regulation is mainly done by kidneys. This, however, takes several hours to days to act, but this is the most powerful regulating system to counter the pH. Now coming to buffers. Now buffers are the solution that resist change in pH by addition of acid or alkali. What are the compositions of the buffers? It can be a combination of weak acid with their salt and a strong base, or weak base with their salt and strong acid. Now how do buffers act? So when strong acid is added to buffer, it gets converted to weak acid. Consider this example: dissociation of strong acid, hydrochloric acid, which dissociates as cation H plus ion and chloride anion. Now this acid is buffered by bicarbonate buffer. Now the bicarbonate part of sodium bicarbonate buffers this H plus ion and gets converted to carbonic acid, which is a weak acid, and sodium combines with chloride ion to form sodium chloride. Now what happens when base is added to a buffer? So this reacts with acid forming salt and water. Consider this base NaOH, and this is buffered by acetate buffer or the acetic acid. Now acetic acid reacts with sodium hydroxide to form the salt, that is sodium acetate and water. Now what is the effective range of the buffer? Consider the Henderson-Hasselbalch equation. pH is equal to pK plus log of base by acid. When concentration of base and acid are equal, then pH is equal to pKa. So a buffer is most effective when the concentration of salt and acid equal. Now, the types of buffers. They can be either intracellular buffer and the extracellular buffer. Intracellular buffer accounts for 58% of the total buffers, of which the phosphate is most important intracellular buffer, contributing to 50%, and the remaining 6% is contributed by hemoglobin buffer inside RPC. Extracellular buffers contribute to 42% of the total buffers, of which the major buffer is the plasma buffer, that is the bicarbonate buffer 40%, and protein and phosphate buffer accounting for 1%. Now let's find out what is the effective range of this bicarbonate buffer. Consider this Henderson-Hasselbalch equation. pH is equal to pK plus log of base by acid. Here base is bicarbonate, acid is carbonic acid. Now all these values are already known to us. pH of the blood is average pH 7.4, pK of carbonic acid is 6.1, bicarbonate concentration, average bicarbonate concentration is 24 millimoles per liter, and concentration of carbonic acid is 1.2 millimoles per liter. Let's substitute all these values in this Henderson-Hasselbalch equation. So pKa 6.1 plus log of bicarbonate is 24, carbonic acid concentration is 1.2. So 6.1 plus log of 2. So 6.1 and log of 2 is 1.3. So it is 7.4. So the effective range of bicarbonate buffer is 20:1. This is because 24 divided by 1.2 is 20. So the effective range of bicarbonate buffer is 20:1. So now let's find out the effective range of this phosphate buffer. Now phosphate has got three ionizable groups. First group is H3PO4, which dissociates as H plus ion and H2PO4, and the pK of H3PO4 is 1.96. Second is H2PO4, which dissociates as H plus ion and HPO4, and the pK of H2PO4 is 6.8. The third group is HPO4, which dissociates as H plus ion and PO4, and the pK of HPO4 is 12.4. Among these three ionizable group, H2PO4, the pK of H2PO4 is 6.8, which is close to physiological blood pH, and this acts as the phosphate buffer. Consider the Henderson-Hasselbalch equation. pH is equal to pK plus log of base by acid. Base here is represented by disodium hydrogen phosphate or the base phosphate, and the acid is as sodium acid phosphate. Now we know all these values. pH, average blood pH is 7.4, pK of H2PO4 is 6.8. Now we need to find out the concentration of base phosphate and the acid phosphate to act it as effective buffer. So 7.4 minus 6.8 is 0.6. Now antilog of 0.6 is 4. So the effective range of phosphate buffer is 4. 1. So this was all about buffers. Thank you. Next video will be on respiratory regulation.